Right. Uh, Good morning once more. And today I'm going to go through the second part of aircraft performance, which is dynamic performance. Last time we spent a bit of time discussing static performance, and today we'll look at dynamic performance, and in this topic we'll look at takeoff and landing performance. Okay. All right. So in this topic we'll look at in the previous analysis we had ignored the acceleration. We assumed the acceleration was equal to 0 and it never played any role, but in here the acceleration is not equal to 0. So if you look at slide 3, where there is a sketch of an aircraft on the ground about to take off, and look at the forces that are acting on this aircraft. We have the weight that is acting on the center of gravity, and we've got the lift and drag as well as the thrust. Then since the tires of the aircraft are in contact with the surface, there is a frictional force that is in the opposite direction to the thrust force, and this frictional force or resistant force is denoted by the letter R and is equal to the coefficient of rolling friction multiplied by the normal force, which is the difference between the weight and the lift. And now if you sum up all the forces parallel to the ground and applying Newton's second law, the resultant force F will be equal to the thrust, which is in the opposite direction, minus the drag and the frictional force. And if you substitute the values for the frictional force, you get this equation. And the right hand side of this equation, which is m multiplied by dv dt, is simply the acceleration. And yeah, then the lift and drag are given by the dynamic pressure multiplied by the area and the lift coefficient, and for the drag the same expression, just substitute the drag coefficient. So this part is not very hard to understand. And now if we assume a constant thrust force and an average value of the sum of the drag and resistant force, which is d plus the resistant force, and if you assume that these are constant and you substitute them with an effective force, which is given by equation 6, then you can have an expression equal to equation 6, which is the effective force is equal to the thrust minus the drag plus the resistant force, because the drag and the resistant force, they're acting in the same directions and they have a minus sign. Then the distance required to move a body of mass m to a velocity v under a constant force F is given by this equation. S is equal to v squared multiplied by m divided by 2f. M is the mass, F is the average force or the effective force. So if you substitute equation 6 into equation 7, then where there is m, the mass, you substitute it by weight divided by the gravitational force, then you get equation 8. And here the subscript L O is the lift off distance. So the lift off distance is equal to the lift off speed. So LO is the lift off, VLO is the lift off velocity, and G multiplied by the mass, which has been replaced by W over G, then divided by 2, then this part is the force. Now, to ensure a margin of safety during takeoff, the lift-off velocity is usually given to be 20% higher than the stalling velocity. And this is so because you don't want the aircraft to stall as it is taking off. That's why the lift-off speed should be 20% higher. And if you do that, you substitute VL in the previous equation, this one, equation 8. For VL, you substitute it with this equation 9, you get equation 11. So in equation 8, VL was squared. So if you square equation 9, 1.2 will be equal to 1.44. Then here there is a W, so if you square this, the square root will get out, but in the previous equation there is a W here, so W times W will be equal to W squared. So don't get confused. And the rest will stay as they are, and you will get equation 10. Then from equation 10 you can make calculations, and this author Chevelle, he made a suggestion that the average force, which in our case is T minus, then in the bracket D plus the resistance force, which is the average force. So the suggestion that Chevelle made is the average force can be set to an instantaneous value at a velocity equal to 0.7 VLO, or the lift off velocity. So the average force can be equated to can be equal to 0.7 the lift off velocity. And from equation 10, if you assume that this aircraft is taking off from a paved runway which has a relatively constant frictional coefficient of rolling friction, which varies from 0.02 for a smooth paved surface to 0.1 for a glass field, then you can also note that from equation 10, the drag and the resistance force, though they are usually smaller compared to the thrust force. So you can make a simplification where these two resistance forces are comparably insignificant to the thrust force. And if you do that, you end up with this equation, like D plus the resistance force, you equate them roughly equal to 0, and you end up with this expression. So this expression shows that the lift off distance is equal to 1.44 the weight squared divided by the gravitational force multiplied by the density, area, lift coefficient, and thrust. And if we look at the previous equation, we can make some deduction that the lift off distance is sensitive to the change in weight. So if you increase the weight, you will increase the lift off distance. From here, from this equation 11, if you increase the weight, then it means that even the lift off distance will increase. And from what we've always discussed, this is why if an aircraft develops a fault prior to takeoff, the pilot will resort to fuel jettison, because it will be practically impossible for him to land with a very heavy aircraft because of this equation. And this is what I've always been telling you in class, that these formulas, you shouldn't learn them for the sake of learning them. They are very applicable. From this equation you can tell, if you double the weight, because the weight here is squared, so if you double the weight, it means you quadruple the lift off distance. So it means if you are landing with a very heavy aircraft, you will require a very long runway for you to land. Otherwise, there has been instances where the runway has been exceeded and that has resulted into a crash. Alright, then also from equation 11 you can tell that this lift off distance also depends on the density. So if you are landing on a very cold day, you need a shorter runway compared to when you are landing on a very hot day, because when it's hot the density is less, and if the density is less, it means that the lift off distance will be greater. And also the lift off distance will depend on the wing area and the lift coefficient. And this makes sense from the equation. Hopefully it does. Right, then now if we consider landing performance, so when the plane is about to land, what you are interested in is you need to decrease speed. So the equations will be the same, but here we'll assume that as the plane is coming to a complete stop, the pilot will decrease the thrust to 0. So from the previous equation, for the effective force with thrust equal to 0, then that equation will reduce to equation 4. Now, previously we had VLO, the lift off speed, but now we have VT, which is the touchdown velocity, and SL would denote the distance required for a complete stop as the aircraft is landing. And now we can integrate equation 12 to get this distance, and again we can make an assumption that D plus the resistant force yields an effective force that is required to decelerate the aircraft to a complete stop. And if we equate this equal to an average force, then and this will have a negative to show that the plane is decelerating as it is trying to stop. And the distance required for a complete stop, it will have a negative here. So So the negative is just there to show that this is the force required to stop. And if we substitute the average force into equation 14, remember the force had a negative sign. Here, equation 13, it has a negative sign. So that negative and this negative in equation 14, they'll cancel out, and the resulting expression for complete stop is given by equation 14. So Vt is the touchdown speed, where there was the mass, you substitute weight divided by the gravity force, and you have this expression. And again here, the remember the lift-off speed, we said the lift-off speed should be 20% higher, that's why that was 1.2, but the touchdown speed, to prevent the aircraft from stalling, it should be 30% higher. And so the touchdown speed will go 1.3, 30% higher than the stall speed. And doing the same like we did previously, we get the expression given by equation 17. And I believe nothing is hard here. Right, now modern aircraft, they use thrust reversal as a means to shorten the runway. Now if this aircraft proud to touch down, the thrust reversing mechanism is deployed, then the previous equation, remember there was zero thrust, but we are applying thrust reversal. It means that the direction of the thrust will be in the same direction as the drag and the resisting force, or the frictional force, and this is equal to the force. So substituting this back into, that was equation 14. If you substitute equation 18 into equation 14, you get this expression where TREV is the reverse thrust. And yeah, so if we do that, we get equation 19. So here there are just few things I'm trying to explain, that to shorten the ground roll, to decrease the lift near or equal to 0, hence imposing full weight. So from equation 19, like, you can make some deduction. If you want to shorten the ground roll or the complete stop distance, if you want to make this distance smaller, there are things you can do. One, you need to increase the area, which ultimately wing area, and increase the lift coefficient. So if area and lift coefficient is increased, then SL will reduce. Then if the density is higher, SL will reduce. Also, if the weight is smaller, that is, if you are landing with an empty aircraft, implying you bent all the fuel, then you reduce this distance. Then the thrust, drag, and frictional force, these are constant. There's nothing much you can do to influence them. Okay, so hope this makes sense. Now let's look at another flight situation, which is turning flight in the VN diagram. So what we've discussed so far has been the linear motion, meaning it's flight on a straight path. But now let's look at flight that involves radial acceleration, which lead to curved flight path. So if we look at this sketch, so this is a plane which is in a horizontal curved path. So a plane will be involved in this kind of motion, maybe if it's about to land on a certain airport, then it has not been granted landing right. The pilot might be instructed to fly around before they process his permission to land. So now, in such a flight scenario, what are the forces that will be acting in a level 10? So this sketch shows a plane which is flying horizontal but in a steady 10. So the forces that are acting on this aircraft, there is the weight, then there is the lift, and the resultant force is towards the center. You can see from this sketch FTFR, the resultant force, which is acting towards the center. So there's a centripetal force that will be exerted. And from this sketch, if the aircraft is to maintain steady flight, it means that the weight, which will be acting vertically downwards, must be balanced by the thrust, by the lift, and the lift in this case will be a component of the lift in the vertical direction, which will be L cosine of phi, the included angle. Alright, and from here you can see that the aircraft maintains a constant altitude, moving in the same horizontal path, but the lift and weight lead to a resultant force R, which will act in the horizontal path towards the center. And the resultant force is perpendicular to the flight path, causing an airplane to turn in a circular path with a radius of curvature R. So under this subtopic, turning flight, we wish to determine the turn radius, like how large or big should be the turn radius, as well as the turn rate. So d theta over dt is the turn rate. And from here, from this sketch, the resultant force R is equal to L squared minus W squared. Then we take square root. You can use Pythagoras theorem to do this. That shouldn't be a problem. And if you do that, you get expression 20. Then there's this term, the load factor, which we looked at in the other course. So the load factor is equal to L divided by W. We briefly looked at this under static in aerodynamics. So the load factor is normally expressed in G's, meaning if the lift is five times the weight, then you can say that the aircraft is experiencing 5 G's. And from equation 20, if you factor the W out of the square root sign, you can get the resultant force equal to W minus W then square root of load factor squared minus 1, because L over W and everything squared will be equal to the load factor. And this makes sense. So the radial acceleration that an aircraft will experience is given by V squared divided by R, which is the radius of curvature, and the resultant force will be equal to mass multiplied by acceleration. But the acceleration that this aircraft will experience in a 10 flight is the radial acceleration, which is given by V squared over R, and M is the weight of the aircraft, which is equal to W over G. So the resultant force can also be given by equation 23. Now if you equate equation 22 and equation 23, because both of these equations are standing for one and the same expression, and if you do that, you will get equation 24, where you cancel out the weight and make R a subject. So the 10 radius is equal to the flight speed squared over the gravitational force multiplied by square root of the load factor minus 1. Then the angular velocity, or the 10 rate, is given by d theta over dt, which is also equal to B over R. And this from equation 24. If you expand this V squared, you say V times V, then you say V over R, then bring the other part on the left, you get this expression, which is V squared over R as the 10 rate. Then this is the 10 rate given by equation 25, and from equation 24 and equation 25 you can observe something, that for maneuvering performance of an aircraft, military or civil, obviously it will make more sense, or it will give you a certain advantage to have the smallest possible 10 radius and the largest 10 rate. So the 10 rate simply means an aircraft should be able to turn very fast, within fraction of second it should turn, and it should have a small 10 radius. So to achieve those two, you need to have the highest possible load factor and the lowest velocity. So less velocity, highest load factor will make sure that you have the smallest 10 radius and the largest 10 rate. If we consider another case of turning flight in which the aircraft initially is in a straight level flight, and suddenly there is an increase in lift, like this sketch. So this is known as a pull-up maneuver, but it's also under the 10 radius. So this aircraft is in this level and steady flight. Now consider a situation where there is an increase in lift, because these two forces, for an aircraft to be in steady level flight, the lift should be equal to the weight, and the thrust should be equal to the drag. But consider a situation where the lift suddenly becomes greater than the weight. It means that there will be a net force vertically upwards. So when this happens, this is known as a pull-up maneuver. And the forces that will be acting on this aircraft are similar to the ones we've just seen in the previous sketch, but in here I will just look at the resultant force. In this case, the resultant force will be L minus weight, L minus W as the resultant force, because the lift is greater than the weight, so the resultant force will be vertically upward. So the resultant force will be given by equation 26. And from here, you can again try to divide through by W, so that you get the resultant force is equal to W open bracket N minus 1. And this is the resultant force, which is equal to mass times acceleration, but the acceleration in this case is the radial acceleration, which is equal to v squared over r. And if you equate equation 26 and 27, you get the 10 radius equal to v squared over g, then open bracket n minus 1, and the 10 radius equal to g open bracket n minus 1 over vn. And please do not confuse the previous equation with this one. This equation is for a pull-up maneuver. The previous equation were for a level steady turn. There is a difference. Okay? And again, we can also look at another turning flight, which is called a pull-down maneuver, which is given by this sketch. So, and this is usually performed by military aircraft. They can do all sorts of maneuvers. But look at this military aircraft, which can do some somersaults, where it flies upside down, and the lift and the weight will be acting in the same direction, that is vertically downwards. So for this case, you can also do the analysis and calculate the resultant force, the 10 radius and 10 weight. And I've just written the expression for the 10 radius and the 10 rate, and I challenge you to prove that the 10 radius and 10 rate are given by equation 30 and 31. I'll leave this as an exercise for you, but it's good for you to go through it, and hopefully it should be able to make sense. Alright? So, consideration of 10 radius and 10 rates are particularly important for fighter aircraft, that is military. So everything else being equal, an aircraft with the smallest 10 radius and the largest 10 rate will have definite advantages in combat. That's why right now, like this, the Sukhoi 57 Russian made, and there's the F-15, which is an American made aircraft made by Lockheed Martin. Those are high performance aircraft with varying capabilities. So which aircraft is best depends on these factors. What is its 10 rate? What is its 10 radius? And the other issues relating to maybe radar signature, that is stealth capabilities, So these are some of the factors that will make an aircraft better performing when compared to another aircraft. Now, from the expression we've looked at for 10 radius and 10 rate, for a steady 10, pull-up maneuver, a pull-down maneuver, we can make some simplification. When you've got n plus 1 or n minus 1, if the load factor is greater, say above 10, 10 plus 1 or 10 minus 1, the difference is not that much to 10 plus 1 or 10 minus 1 and 10 plus 1. The difference is minimal. And in that case, the one, we can safely ignore it. And when we do that, the 10 radius will be given by v squared divided by gn, and w is equal to gm over v. And so these are simplifications. You can get errors, but those errors are not that significant, and we can safely ignore them. So once we do that and substitute this expression in equation 34, 21, 32, and 33, we'll get this expression, equation 35, for the 10 radius. And if you further simplify equation 35, you will notice that here there is S wing area and there is the weight. So the lift, which is on both the numerator and denominator, these will cancel out. So the left hand side of equation 35, when you simplify it, you get equation 36. So from equation 35, you can notice that W over S is a design parameter, which is called the wing loading. And if you do the same for the 10 radius, you can simplify it and get this expression. The numerator under the square root is W over S, which is the wing loading. And this gives you equation 36. So from equation 35 and 36, it can be deduced that airplane with lower wing loading will have smaller 10 radius and larger 10 rate, everything else being equal. However, the design of wing loading of an aircraft is usually determined by other factors. So this is not your primary objective, to design an aircraft with higher wing loading, but this will come as a result of other factors such as maneuvering, how much payload can be accommodated by an aircraft, how long, the range, and the maximum velocity. Right? And if we examine equation 35 and 36 for a given aircraft with a given wing loading and ask for this specific airplane, under what condition will the radius of curvature be minimum and the 10 rate maximum, then these answers from this equation clearly R will be minimum and the 10 rate will be maximum when both the lift coefficient and the load factor are maximum. That is, so from equation 35 and equation 36. So from equation 35, the 10 radius will be minimum when the lift coefficient is maximum. Then the 10 rate will be maximum when the load factor is maximum. I hope this makes sense. Everything else being equal, you can make that deduction. And this is exactly what equation 37 and 38 is trying to highlight. Okay? So some practical constraint on what we've just looked at is low speed and you want maximum load factor. So the load factor can be given by this expression, the lift divided by the weight, and the maximum load factor will be obtained when the lift coefficient is maximum and the wing loading is minimum. So at higher speed, the maximum load factor is limited by the structural design of the aircraft. So these considerations are best examined using slide 24. So this slide 24, this is the VN diagram, or velocity load factor diagram. N is the load factor, so velocity load factor diagram. In aerodynamics, we had discussed the load factor diagram, the velocity load factor diagram, but this is a very important topic both for aerodynamics and for aircraft performance, and it is for this reason that I'll repeat the discussion again. So if you look at, so I would encourage you to look at this slide, take a bit of time, study it, and make sense of the explanation that follows after it. So the curve AB, so this AB, A starts from the origin A, and B at the edge, almost at the edge where there's this shaded, the beginning of the shaded line AB. So the curve AB, look at the curve AB, is given by equation 39. This equation 39, which is just above, for maximum load factor. Consider an airplane flying at velocity v1, which is shown in that slide, and assume this aircraft has an angle of attack such that lift coefficient is less than the maximum lift coefficient. This flight condition is represented by point 1 on the slide. So this is point 1 on this slide, and assume that the angle of attack is increased to that for obtaining the maximum lift coefficient, keeping the velocity constant at v1. The lift increases to its maximum value for the given velocity v1, and hence the load factor n equal to L over W reaches its maximum value n max for a given v1. This value of the maximum load factor is given by equation 39, and the corresponding flight condition is given by point 2 in slide 24. So point 1, point 2. So point 2 is the maximum lift coefficient that can be reached when flying at a velocity v1. Alright? And this value of then this value is given by equation, okay. Point 3 in slide 24 is an obtained in flight. So if v2 is, so if an aircraft is flying with velocity v1, the maximum lift coefficient that it can attain is only possible at v2. So v3 is outside what is practically attainable, and hence it's not a feasible point. Okay, so that's what this slide is trying to explain. Then the previous slide, then now as v1 is increased, so now if you increase the speed from v1 to say a value v4, which is here, to say v4, we've increased the speed, the maximum possible load factor also increases. So the maximum possible load factor, when you increase the speed, even the maximum possible load factor will also increase, because the maximum load factor, there is a speed component. Look at this equation 39. It has a velocity component. So if you increase the velocity, even the maximum load factor will have to increase accordingly. All right? And so if you increase the maximum, if you increase the speed, the maximum also increases as given by 0.4 and is calculated from equation 39. However, the maximum load factor cannot be allowed to increase indefinitely beyond a certain value of the load factor, defined as the positive limit load factor, and shown as the horizontal line BC in slide 24. Structural damage may occur to the aircraft. So from here, I said if you increase the velocity from V1 to, say, a new velocity V4, even the maximum load factor will increase as given by equation 39. However, there's a practical limit above which the load factor can increase. Beyond that, structural damage can occur, and this limit is given by the line BC on this VM diagram. So BC is the practical limit that the load factor can reach. So from here, it's not possible to reach velocity V5, because 5 is in the region of structural damage, and no sane pilot would want to compromise the structure of the aircraft. Hence, you need to fly within the safety margin of what the aircraft was designed to do. All right. Now, the velocity corresponding to B, which is the ceiling beyond which structural damage will occur, below which you are in the safe zone. So the velocity that corresponds to point B on the VN diagram is designated V with a star. At velocities higher than V, say 5, the airplane must fly at values of lift coefficient less than the maximum lift coefficient, so that the positive load limit is not exceeded. If flight at the maximum lift is obtained at velocity V5 corresponding to 0.5, then structural damage occurs. So I've already explained this part. Then the right side of the VN diagram, line CD from this slide, CD is a high speed limit. At velocities greater than this, the dynamic pressure becomes too large, then again structural damage may occur to the aircraft. Okay, so CD, this is the speed limit, like the maximum speed that this aircraft can fly at. Beyond this, structural damage will occur. Below it, we are still flying in the safe limit. Okay, so the structural design of most airplanes is such that the maximum velocity allowed by the VN diagram is sufficiently greater than the maximum diving velocity for the airplane. Okay, so then the bottom part of the VN diagram given by curve AE. So AE, so when the aircraft is flying with negative absolute angles of attack, then it will have a negative load factor. And when that happens, it means that since the load factor N is equal to L over W, if the lift is negative and the weight is positive, then you have negative load factor. Again, just as I explained on the line AB, where you've got the store area, even when the aircraft is flying with negative load factor. There's also the store region, which is given by the area under this curve AE. And what else? Yeah, at absolute angle of attack less than 0, the lift is negative and acts in the downwards direction. If the wing is pitched downwards to a large enough negative angle of attack, the floor will separate from the bottom of the wing, and the downwards acting lift will decrease in magnitude and the wing stall. So the line ED gives the negative limit load factor beyond which structural damage occurs again. So this is pretty the same as what I earlier explained, and I would encourage you to just study it and make sense out of it. So finally, let me look at that velocity v star, which occurs at B. Remember, B is the threshold. Above B, structural damage will begin to occur. Then below B, you are in the safe zone. Now the velocity beyond which structural damage will start is given by this expression, equation 40. So at velocity v star, you've got the maximum load factor and the maximum lift coefficient. So the value of the maximum load factor corresponds to that point at B, the corner. Velocity is an interesting dividing line. At flight velocities less than v star, it is not possible to structurally damage the airplane owing to the generation of too much lift. In contrast, at velocities greater than v star, you obtain lift that can structurally damage the aircraft, such as 0.5, which is in the structural damage zone, and a pilot should ensure that he avoids such a scenario. Alright, I think this is the end. This is a summarized end of dynamic performance, and this part of accelerated rate of climb, I already sent the handout on this part, which I believe you've had time to start, and hopefully I'll prepare some recorded video on it. And what will follow next is an assignment on this topic, and yeah, have a good day, and please take time to go through what I've just explained, because this is examinable. And have a good day. Thanks.